To a wide-in quick chat from the initiative in Computational Humanities, Arts and Social Sciences through the Faculty of Computing and Data Sciences at Boston University. Today we'll be hearing from Dr. Andrew Bell. Dr. Bell is an assistant professor in the Department of Earth and Environment at Boston University. He studies livelihoods and resource decision-making, including domains of irrigation, pest management, ecosystem services, technology adoption and migration. Most of his work applies survey and experimental tools such as games, high-frequency smartphone-based surveys to model behaviour and to build agent-based models to understand what these behaviours imply for system-level outcomes under scenarios of environmental change. Please welcome Dr. Bell.
Hello. So I don't have slides prepared. I do have some materials that may or may not be useful, and they are hidden behind this link, bit.ly/bell_abm_April23, or through the QR code there. And those are some of the same materials that I use or will use in my course offered this fall, CDS 541. The goal of which, and similarly to the goal today, is just to kind of make ABM seem interesting and accessible. So I'll go back and forth between some of the materials that I've set up there at this link and NetLogo, which is a wonderful teaching platform for agent-based models. Agent-based modeling is a tool that, you can do with just about any platform you might like. It's a tool to apply for problems where we believe the outcome that we're interested in a system is emergent from interactions among individual agents within the system and interactions among them and their environment. So, for example, perhaps we're interested in overall traffic safety and traffic outcomes emergent from the way individuals drive and interact with other drivers. Or we're interested in understanding the outcome of an election, which is going to be an outcome of the way people vote in response perhaps to a whole range of different beliefs along with the way that they interact with each other. Or maybe we're interested in the environmental domain and say like the amount of sediment we can expect to be eroding into a watercourse that emerges from the way farmers in coordination with each other in many cases coordinate to maintain riparian cover for that waterway. Lots of different problems to look at, lots of different disciplines engaged in different dimensions of agent-based modeling. And so what I want to do, and I have, I guess, probably about 15 minutes or so, is I want to show just a couple of fun little examples to help make clear that link between some simple individual behavior or some individual interaction and an emergent outcome. And so one of the things that, if you've thought about this before or read about it or practiced it, you might have come across the description of like bird flocking as this really cool example of emergent behavior. And I'm going to pull up a model that I didn't make. It came with the toolkit. And in fact, for any of you who are listening or watching, if you wanted to just get onto Google and download NetLogo, it'll take you just a minute to pull it up. And NetLogo will come with a library of models that have been nicely validated over the several decades that it's been a valuable teaching tool. And it's easy to pull up lots of different things. I'm going to pull up the flocking model here. There it is. I'm going to open it. And it was already open. But here we are. Whenever you open up a NetLogo model, you're going to be presented with a couple of different interfaces. So this first interface is all of the tools, all of the control elements we have for our model, and all of the display elements that we have to look into what's happening in our model. We have another tab here that describes what's happening in our model if the designer of the model has taken the time to put it in there. And then in the back end, we have our engine, all of the code that's shaping what's happening. The NetLogo code, for those of you who are coders and maybe you learned in Java or C++ or newer languages like Python or other things like this, they're all kind of the same. They're all good at different things. One of the things that NetLogo is really, really good at, sort of comparative advantage, is invoking sets of agents or invoking sets of objects. So in a very conversational style, it can say, hey, ask all of the agents wearing red sweaters to go and do this, and ask all of the agents who are standing on this side of the line to go and do that. That sort of operation is very easy and quick in NetLogo, which kind of makes it really well suited for agent-based modeling. So this is the basic flocking model that comes with NetLogo, and it describes very simply what's happening. You have birds that are making decisions to be close to all the other birds that they see, but not too close. And if they're just the right distance, then they're just going to try and steer themselves to go with the other birds. That's it. And on its own, you might expect that that leads to birds flocking. It seems somewhat intuitive, but we can have a look and see. So we'll set up our model. There's a little setup button. We've got a bunch of little triangles here that are birds of slightly different colors. And we've got a bunch of parameters that if we were spending more time together, we'd dig into in more detail. But for now, we're just going to run the model. And we're looking. It sort of looks like things are happening, but this is really slow. We don't have a ton of time. So let's speed up the world a little bit. Let's go a little faster. And we're starting to see birds moving together. I should be clear that the edge here is the edge there. This is a torus that wraps around. And it looks like in a reasonably small amount of time, our birds have found each other, which is wonderful. And they form these sort of small groups moving around in space. So really simple rule leading to predictive, it's an emergent behavior at the system scale. Super fun. Lots of other cool examples we can explore that are just looking at animals, bugs, nature, what's happening. I want to pull up one other example that's fun, and that is the ants model. Anybody in the room know what ants, how do ants do things? How do ants go about their lives? Right. And where do those pheromones come from? The other ants. And what do the pheromones say? Follow me. Perfect. All right. We got a perfect model of oops, not that one, of ant behavior here. So there we go. So in this model, we have in the middle, we have an ant home, and we have a few food piles. And the ants do exactly as your colleague described. They wander around randomly until they find something. And when they find it, they pick it up, and they know how to get back. And then they send a signal. They're like, hey, follow this. And so the ant's job is to wander around until either they find food or they smell the signal, and then they kind of hill climb, follow the signal, follow the increasing direction, the increasing concentration of pheromone. So when you run this model, here are ants running around, and the little green trails here are our little bits of pheromone. And you see where there's these sort of clear patterns of pheromone, we get really clear behavior, and then all the food's gone, and then it's just a little bit of chaos for a moment while the ants reorient. Oh, and they found the last one. And what's fun here is we can experiment a little bit. Let's start over again. Let's make a world where it evaporates really quickly. This is a bit of an unkindness I'm performing on the ants here. But you know what I mean? It's taking a lot longer for them to find. So we can kind of, if we wish to, we could perform experiments with something like this to understand like how important evaporation rates are and environmental change as it then mediates evaporation on ant survivability or whatever other thing it is. Now, not all the problems that we would wish to look at are things running around in space. Imagining that we want to move out and look maybe more into the behavioral side, there are lots of cool models you can build with modeling people running around, but most of the things that we're interested in capturing are playing out over long periods of time where I actually don't care so much about what you're doing at every moment of your day, but I care about some set of decisions that you're making and perhaps some set of interactions you have with others. And possibly, I think, the first sort of agent-based model of human decision-making that I know of goes back about 60 or 70 years, and it's Thomas Schelling's segregation model. So if you've read about agent-based modeling of people, you've probably read about this model. There's a lovely implementation of it here. There we go. Spelled it correctly. And here we are. So in this model, this is, Thomas Schelling built this like this is pre-computers, definitely pre-net logo. This was solved with like coins on a sheet of paper and very careful note-taking over like days and days and days. But it was a response to this sort of prevailing belief that segregation where it emerged in cities was born of intolerance. And so Schelling's model kind of questions that a little bit. It's a very simple model. There are two types of agents. They're two different colors. Here they're orange and blue. And they are happy when some fraction of their neighbors are the same color as them. And here I think that the happy agents are squares. The unhappy agents are X's and are going to be looking for somewhere else to move. And if they're unhappy, they just move randomly. They find some spot they can move to, and hopefully that works out for them. If they're unhappy still, they might move again. And the one parameter that we have to manipulate is this, how similar do agents want their neighbors to be? And you can see very easily, so let's set this model up. We're going to set up a rule of about 68, 66. So I want 2 out of 3 of my neighbors to look like me. When I say that, does that come off as a tolerant or an intolerant sort of worldview? Right. I need to be surrounded by like, right? That's how I would interpret that. And when I run this model, off we go, and I'm going to speed it up a little bit. And again, this is a torus, so where the world ends here, it begins anew over here. We end up with these little enclaves that, oh, we've lost them. Okay, and our model stopped. So really what we have here is a block of orange and a block of blue, right, connected through this side. And I probably would have expected, I think we all did. But the thing that you may not have expected is that as individuals, this desire to have 2 out of 3 of our neighbors look like us led in the aggregate for us to have 99.9% of all of our neighbors look like us. So this emergent property at the system scale isn't something that we would have easily predicted. So here's where, I mean, that's not the famous result. I'm going to show you the famous result. Let's flip this around a little bit, and let's say, imagine I say, look, I'd love to have 1 out of 3 of my neighbors look like me. I'm fine to be surrounded by difference, but I want to feel some connection with people around me. Now, I'm leading you a little bit. I said that in a nicer way. But I'm trying to get the idea that we might interpret that as like a tolerant worldview. And when I run this model, what do you think I'm going to see? Something probably pretty similar, yeah? I mean, I've kind of primed you as a crowd, but let's see how we do. This solves pretty quickly. And you might say, well, this is a different world. But we do still really clearly see these patterns of segregation. And importantly, our desire to have 1 out of 3 neighbors look like us led us to a world where 3 out of 4 of our neighbors looked like us. Again, that's that emergent property where this thing that we thought of as tolerant led us to a world where we're still very segregated. Now, across the world, like cities across the world are segregated just like this. Some of this, well, probably some very small part of it is choice. A lot of it is structural, a lot of it is historical, and people's decisions about what they want around them may have a very small part to do with it. And this isn't Schelling saying, look, this is how segregation happens. It's him saying, look, here's a plausible story where segregation emerged even in the absence of what we would consider intolerance. So let's be more critical about how we think about what must be or what has to be. And that's part of what made this a really famous result. So these are sort of simple toys. I have 10 minutes, right? Ish, 5, 4, 7. All right, we'll go with 7. I have 7 minutes. You can do much bigger things with this, and I'll show just a couple of slides from kind of like a Schelling-inspired example, modeling project that I've built. This is the Daisy, there we go. The MIDAS model. This is migration, intensification, and diversification as adaptive strategies. You have to have a cool name for a model. That's what I landed on. And in this model, we have agents living in different places, embedded in social networks and sharing information and resources across each other, deriving utility from what we're calling utility sources or utility layers in a place that you could think of as income, but also use value or nature or time with my family or whatever it is that you could imagine people deriving value from. And they are periodically making decisions about what's the best thing for me, what's the best portfolio of opportunities for me. And in the case that the agent decides or realizes that the best set of things for them is somewhere else, then they move. And so this is a sort of a case in which migration then and migration rates are emergent out of the sort of set of opportunities that are available. And so when I built this, and it's a number of years ago now, it was one of the first to sort of simultaneously consider all of these different things that matter, that shape our livelihood. So push factors, right? Something that's not working for me where I am. Pull factors, my knowledge of something that's good somewhere else. And then moorings or intervening factors, the sort of kinetic barriers that keep me from moving. Like I have family here and I own a car and it's a weak market or whatever it is. And then importantly then, migration can emerge as this emergent strategy. There's a kind of a lot of stuff in there that is meant to try and capture both sort of like an underlying, core real-world time scale of like nature advances, the sun goes up and down, we get paychecks on regular intervals, with the sort of other things that are not moored like that. We don't with any regularity talk with our friends, unfortunately, or spend time in nature, or have children, or get married, or all these other things. So trying to sort of capture a range of different things that people experience We have sort of probabilistically agents might die, have children, meet new people, talk to other people, learn things about the world, make some decision to make a life change, all while inexorably underneath that they're deriving utility from their jobs or whatever it is. I'll probably skip quickly through stories about how they make decisions, but it's basically boundedly rational comparison of some small number of portfolios in different places, making a decision about what's best for them. And in this particular case, we had a nice application where we looked at migration between districts in Bangladesh under different stressors of sea level rise. Again, sort of like responding to this idea that when the sea level rises, we will observe this exodus from coastal spaces. And what we were able to show is, because a lot of the amenities and opportunities that are available in coastal cities where we've invested a lot are likely to persist through sort of like mid to near term sea level rise, even though we will experience some stress, some damage, we don't see enough to suppress migration towards the coast through the coming decades. So again, this is not us saying that's what's going to happen. It's us saying we have to be a little bit more critical when we say everybody's going to flee the sort of like flooding of the coastal region. So in my hopes and dreams, it's a bit of a Schelling-esque result. I have a couple of other examples that I'd love to show, but maybe I'll save them for another time and just stop for a moment and highlight some kind of cool research frontiers in agent-based modeling. So I've done that thing where it's split me into two screens, so let me just figure out where that is. There we go. Okay. So these are the materials that I shared, some textbooks and readings listed. But I'm going to pull up a couple of things here as I talk. So as cheap computers, or as good computers become cheap, there are all kinds of cool things that we can do. I showed some silly toy examples, but it's not impossible to build models with millions and millions of agents. And I'm sure there are smart technical people in the room who know how to use graphics cards to do a lot of like really fast processing. And there are cool models in the epidemiological space where we model like millions and millions of people making decisions about whether to go in or out, or wear masks or not. But we do get to kind of a limit where more agents is just noise, and it's not necessarily capturing more people, but trying to capture sort of more scales of decision making and more layers of institutions. And so another cool frontier in the agent-based modeling space is figuring out how to do that, how to capture deliberative governance as a thing that people both participate in and are shaped by. But the challenge is, how do you scale that decision, the sort of governance decision making against the way individuals make decisions and interact with each other. So that's another cool frontier. There are kind of cool things that are being done with making just much more complicated agents. So for a very long time, the sort of like the frontier of really fancy agents were the belief, desire, intention agents, where we sort of have really sophisticated models for how agents make decisions based on things they believe and intend to do, and they're informed by big databases, big data sets on what we think agents would know and how they would their thinking would be trained. Although a lot of that is kind of just disappeared now in the world of large language models, and I want to show you something cool that just came out. This is 4 days off the presses. This is scrolling down this list. Here we go. This is a working paper of a small number of generative agents using full natural language trained just like ChatGPT or whichever it is, where you as a user can interact using full language. So it's almost like, imagine you're playing The Sims, but you literally can talk in any way you wanted to any of the other Sims, and they can talk back, and there's stuff going on between them that you're not even going to notice. It's pretty wild. It was described where I saw it as Westworld. This is much more adorable, of course, than Westworld, but this is kind of this really exciting frontier, or one of the many frontiers in agent-based modeling. And the last thing that I'll highlight, all of this stuff is really cool. Lots of different people and lots of different disciplines do agent-based modeling. We have lots of different assumptions. And one of the things that hangs us up as a discipline is that it's pretty rare for the decisions I made in making my model to be useful for you or you or you. And so we get sort of stymied in our ability to share tools. And so there's a lot of work going on to sort of figure out, like, what's the sort of atomic level at which we are best able to share agent-based modeling tools, decision rules, underlying pieces, so that we kind of not only make better use of existing tools, but also converge upon sort of common rules and common architecture for doing agent-based modeling. So that's a little bit of what you can do, a little bit of what the frontiers are, and I'll probably stop there.
Thank you. That was splendid. A great introduction. This last type of model you showed with complex agents that can communicate, have you studied this or dug into it?
No, I mean, I just
You just found
that.
it 4 days ago?
Yeah.
So tell me what you could do with something like that. If you had communicating agents, would it help you understand the dynamics of the model or not? It seems like a lot of what agents would be thinking and able to talk about might not really reflect the dynamics of the model that you most care about. So how deep is this really?
I mean, it's hard to answer your question without answering thinking about the bigger question of, like, what does ChatGPT do for us, and what does it mean? And I don't know. I think as modelers and as scientists, often we are looking for explanations rather than simulations, right? We're more looking for something where we can identify an effect than we are looking to be immersed in something that feels real. So I don't know. Certainly this doesn't fit any of my research goals, so it's a little difficult for me to answer that question. Often with simpler agents, we're looking to sort of like pull from their decisions, you know, sort of like a life history, and understand, what does this mean, and what does this kind of agent look like, and how do they fit into the sort of real people that we observe and real decisions we expect people to make. I think it's absolutely correct that a lot of this stuff doesn't necessarily have bearing on stuff we care about. I don't mean to dismiss it as research. It's just not a research domain I know a ton about.
So this was great. I use NetLogo. I really enjoy it. And I think my constraint, and I think this is a typical thing that people who use agent-based modeling come across, is when do you stop? Because there are so many variables you can create. There are so many sliders. Every conceivable thing can be made into a continuous variable. When do you stop? And the second thing, I'm really intrigued by this, is given realistically how little we know about how the human brain functions, the creation of this sort of, I'm reading it from your screen, believable proxies of human behavior, it's somewhat stunning to me, and it's really intriguing, but it is somewhat stunning to me.
Yeah, it's a good question. So one of the things that I think the thing that I spend the most time with my own students on is this challenge of what goes into your model. And really the simple answer is things that vary importantly with respect to your question belong in your model, and things that don't belong in your model. But that's a really simple way of saying a kind of a difficult thing to evaluate. And whatever discipline that we're in and whatever we're building, answering this question of, like, how can we block off variation, or should we block off variation, it's a challenge. And that's really the skill of the modeler, is going from, in the same way whether you're building a model or not, going from question to testable hypothesis means finding a way to identify and explain variation, and that's really what you're doing when you build a model.
That also makes me think about like when connecting simulation with like data science or prediction. You know, like you have all these parameters, but then you have to like say, okay, what's an actual reasonable parameter of value for these parameters based on, like, say, data or something. I know that seems like a very, I don't have any sense of how that process tends to go.
Yeah, that's a great, and really in a lot of ways, in the absence of data or in the absence of theory, our models are just toys and games, right? I think one of the challenges is that when you say data and model, those are really kind of 2 points along a spectrum that really is better sort of broken apart as observations and theory, or observations and rules, right? So data is already a model, right? We've made all kinds of assumptions to decide how to collect it, what matters, how to clean it, how to organize it. So it is in itself already a model. And when we talk about models like this, they are often somewhat inspired by theory or informed by theory, sometimes informed empirically, and it's kind of just a a messy mix of things we think of as mechanisms, which is really just theory that we've backed up pretty well, and empiricism, which is, things we haven't explained particularly well yet. So I would say, to the extent that you have observations that help you identify meaningful ranges, great.
Thanks.
So the talk is titled something about agent-based modeling for policy evaluation. So how do you balance building models and looking into things that you are interested in versus building models and looking into things that policymakers or people related to policy are interested in?
Oh, that's an excellent question. And I had forgotten actually the title of the talk. Maybe I went the wrong way, but hopefully this was helpful. So one of the things that we do in my group is this sort of like process of like knowledge brokered model development, where typically across like a workshop of like several days in duration, where we start with like training and systems thinking and making conceptual links across processes that we think would matter, coming to a point where maybe a group of modelers and non-modelers agree on what's an appropriate conceptual model to describe, the question we care about in the set of processes that matter. And then it's kind of a long engagement to sort of have a technical team that's operationalizing your model, but then tying back in with the people who aren't building it to say, hey, this is how we've made this idea real, this is how we've made this idea real, this is this thing that didn't work in the end, so let's chat about that. But it is challenging, because in the end, you have people that need to make decisions, and their headspace is not the same as the modeler's headspace. And so finding a way to communicate the sort of layers upon layers of assumptions to someone who's then making a decision is almost impossible unless you've kind of spent that time beforehand sort of co-producing the model.
You mentioned bounded rationality at one point. There are a lot of economic models that use the assumption that agents are fully rational in the way they make decisions. Game theoretic models, for example, are frequently of that kind. But we know with high certainty that human beings don't actually behave that way. Their judgments are affected by their values and their environments in very profound ways. How do you communicate with the other modelers who have rational agents instead of boundedly rational agents? What does that debate look like, and how do you integrate awareness of that debate into the way you design agent-based models?
No, that's a really good point. I'm going to give an unsatisfying answer to this, so one of the challenges we always have as modelers is whether we've got, whether we have rational agents or boundedly rational or whatever, we have some simplification, right? We have some very simple representation of real behavior in a real system, and ideally there's some good literature or policy benchmark that we can compare our findings to. So the rational model helps because we have a long history of using the rational model. And so we can say our model, when we applied this rational thinking, gave us this result, which is what you've seen here and here and here. And if I want to take it one step further and have boundedly rational agents, I can make that extension and say, when we move from rational to boundedly rational, this is how my finding changes. And then really the next step is to say, we know that this is still a model and we know that people are different. How do we expect the system to behave differently when we relax all of the simplifying assumptions we made in our model? That last step is really important, and people don't do it. And this is the challenge. This is how modeling outputs get treated like answers or oracles when really they shouldn't be. We know that people aren't rational, but it's a helpful benchmark because there's a lot of history to it. And it's relatively easy to interpret. But making that next step of what happens when we relax that assumption and move to real people is this critical part that gets left out of it, I think, a lot of the use of modeling findings.
One final question having to do with the ethics of modeling. All of the assumptions that go into these models that you build with the intention of helping policy professionals make better decisions, those assumptions are difficult to communicate. Sometimes policy professionals glom onto the model and forget about the fact that it's got limitations. How do you handle the ethical responsibility to make sure that your model isn't taken too literally or beyond the scope of what its assumptions allow?
It's a tough question. I mean, I am so lucky to labor in anonymity and irrelevance that I haven't really had to confront that challenge just yet. I mean, I think, and again, unsatisfying answer, but it ties into this broader question of like, even just getting technical knowledge into the room is hard. And then you have the sort of like in the room effect of, what ends up happening really just depends on who was there. Whether or not they were able to be informed by technical knowledge or modeling, it can be just power asymmetries in who you chose to put at the table that matter more than anything else. And so I don't have a really satisfying answer to that sort of ethical obligation, but I am very interested in thinking through, like, what are the best ways to make the space for technical knowledge at the table? And then from there, maybe do a better job of answering that question.